Okay, I think we can start. Hello everyone. Welcome to this pre-start to the ICONS conference. Good afternoon, good morning, good afternoon, good evening, depending on where you are. So we're happy to have this pre-start to the conference with a very exciting tutorial from Jason Eshraghian, who's joining us actually from Australia right now. It's pretty late there, so we're very grateful that he accepted to join us. He is currently a postdoc and a Fulbright scholar at the ECE department of University of Michigan. He has very different contribution to the field of neuromorphic engineering, all the way from devices to hardware, to algorithm, codes, even applications. So he has his foot everywhere, and he has been developing this library for training spiking neural networks in the past year, and we're very excited to hear a tutorial about it and to learn more. So yeah, without further ado, please go ahead, Jason.
Thanks so much, Malika and Katie, for organizing this thing. Thanks for the intro. Always love hearing about myself. Look, if you're wondering what spiking neurons are, how to implement backpropagation in deep learning algorithms, then you're definitely in the right place. If you already know how to run SNNs on deep learning algorithms, then hopefully you can still take away some practical lessons that I've kind of picked up on in the past year of developing snnTorch. And given that we're all at this ICONS conference, what's kind of nice is that I guess we're all, in a sense, neuromorphic engineers here. We all believe in the spike, or at least most of us probably do, or hoping to learn and maybe be persuaded as to the utility of spiking neurons. So of course, I think we're all quite familiar with the fact that neural nets trained with deep learning are currently the state-of-the-art algorithms in a lot of AI and ML tasks. So things like natural language processing and computer vision, any sort of high-dimensional data, it seems like neural networks and deep learning are dominating it. And a lot of that success is thanks to the backpropagation algorithm. Now, of course, the cost that comes with the backprop algorithm, comes with this insane scaling of neural nets, is insane. Literally, it's insane. Training the GPT-3 algorithm was $12 million US in power bills. Of course, it's very powerful, but if you compare it to training the brain, now Simon Thorpe had a really cool little analogy here, where if we were to train the brain on an equivalent sort of setup on the world's most powerful supercomputer, we're looking at, I guess, 8.6 times 10 to the 10 neurons multiplied by each of them. Let's average out to 7,000 synapses a fan out each. And if we want to capture the state of the brain with a 1 millisecond precision, right, then we need something with 600 petaflops. So can we do that? Can we achieve that with today's compute? Well, currently, the world's most powerful supercomputer, the Fugaku, can only run 442 petaflops. And what's the cost there? That's 30 megawatts. So a little bit of a disparity with the brain, which is sitting at 12 watts. So one of the primary reasons for that is because I suppose that you could say that in the brain, the circuit itself is the algorithm. Right? They're physically they're not just physically co-located, but they're kind of the same thing in a sense. Now, we don't quite understand enough about the brain to go there. I mean, we can take some lessons from it in order to build better hardware. But in the meantime, I see one of two directions kind of being plausible. A, we could perhaps extract the brain's algorithm using, I suppose, computational neuroscience. We could go down the road of implementing STDP and Hebbian learning. And all of those are quite interesting and have given us a lot of nice insight into what the brain can do and how we can make it useful. Or alternatively, we can use an algorithm that we know works, right, such as backpropagation, and see if we can kind of make it fit with elements of the brain. And in doing so, perhaps extract the best of both worlds. So biologically plausible or spiking neural nets, optimized using the backpropagation algorithm, gradient descent. Right, so just a quick outline of what I'll hopefully be able to teach you over the next 1.5 to 2 hours. See if I can get through it faster. First, we'll start off with discussing what's so good about the brain. I mean, it's kind of clear, but go through it. Then we'll dive into a little bit of semantics with snnTorch. We'll look into spike encoding, rates, temporal encoding, delta modulation, touch on the war between the two factions of spike-based encoding. We're going to dig right down deep into the leaky integrated fire neuron. This might be familiar for a lot of you, but I guess this is a nice way to start off the Icons conference. So we can all start off with an equal platform, and then we'll look at gradient descent on spiking neurons, on how to implement backpropagation on non-differentiable functions. And we'll also look into variants of backprops, such as real-time recurrent learning, a little bit on neuromorphic benchmarks, and a few fancy techniques that have helped me train better networks that hopefully I can impart some of this wisdom and experience that I've amassed by digging down into this rabbit hole through this Zoom screen, right? So yeah, we'll start off with what's so good about the brain. Now, I want to talk a little bit about what I like to call the 3 S's, right? So we'll start off with the first S, spikes, right? Biological neurons interact via single bit spikes, okay? So say I'm an experimentalist. I've got this electrode and I stick it into this neuron, right? Right here, we've got this nice neuron. Now, if I was to put it into the membrane, into the soma, now the voltage would fluctuate, right? I'd get some noise, I'd get some accumulation of inputs. I'd see fluctuations in voltage. But the moment I take it, say, a millimeter away from that neuron body, all of that signal, all of that noise is almost completely attenuated. The only thing that I'm going to be able to measure on that axon is what's called an action potential, right? And so these neurons are clearly communicating with some triggered events. Otherwise, the axon is quiet. There's not really much of a signal until there's an action potential. So action potentials, they vary a little bit from neuron to neuron, but overall, we kind of treat them as stereotypical, identical events. Rather, we're more concerned with the occurrence of an action potential, just that burst in voltage. We're more interested in the fact that it occurs rather than what its makeup is, what its shape is. And so we tend to approximate that in neural encoding studies, or when we take it to deep learning, we approximate it into a single event. And that's characterized by this, as this arrow or Dirac delta-esque function. Right? Now, why might we want to do that? Why do we want to approximate it to this 1 or 0 event? Right? If we take 1s and 0s, and put them into a microprocessor, and operating on them is unsurprisingly very, very easy. Right? Just for argument's sake, let's say I want to multiply this spike or the absence of a spike with a number. 0 times x is going to be 0. 1 times x is going to be x. So we're trading multiplication with just a simple memory readout, right? So no carried propagation delays in the whole multiplication process of digital logic. Just a memory readout, and that's kind of nice. It's certainly a lot nicer than handling floating point or high precision values. So that's one really nice feature of spikes that translates directly over to hardware. Now, the next S that I want to dig into is sparsity, right? Biological neurons spend most of their time at rest and setting most of their activations to 0 at any given time. And I think that was made clear by the previous slide where we had all those zeros, a 1, spike time, and then a bunch of other zeros. Unsurprisingly, it's a lot more efficient for me to describe this list at 7 at position 10, 5 at position 20. It would be super redundant for me to list everything out to you and say 0, 0, 0. That's just pointless. It's a waste of everyone's time. Computers tend to agree, right? Now, in this type of sparse data structure, the memory is only going to increase as the number of non-zero elements increases as well. And so this data structure, it's a very good fit for spikes, and we can kind of exploit that in spiking neural nets, and I suppose in application-specific integrated circuits that are tailored specifically to leveraging sparsity. Now the final S, static suppression, right? more familiarly known as event-driven processing. So this is the idea of where the sensory periphery, so it's my eyes, my nose, my skin, my haptic feedback, it's only going to process information when there is new information to process, right? So let's say we've got this scene here. We've got this car, it's driving along in this beautiful landscape. The motion of that car, well, according to this theory, the motion of that car is going to be captured, right? The static background is suppressed. And in doing so, there's kind of that sparsity advantage again, right? So let me illustrate that example. So the dynamic vision sensor was used to record this, and the dynamic vision sensor is also colloquially known as the silicon retina because it takes advantage, it takes inspiration from the retina. But you can see throwing this football, you're only catching the motion of the football. We don't care about the background. All of that is suppressed. So every pixel is asynchronous to one another, right? All of this is some sort of event-driven paradigm that only responds whenever there's a change. And thanks to that, thanks to the fact that all of these pixels are suppressed and the absence of some sort of global shutter, what you're able to do is achieve substantially lower power consumption from these dynamic vision sensors. And that allows you to, in turn, crank up your clock speed and get this kind of microsecond temporal resolution. And so that's really nice. That's a really nice advantage of dynamic vision sensors, right? So in summary, spikes are great. Now, how have people been using spikes to train neural networks? I guess that's the next thing that we want to explore. So the first and perhaps one of the more mature approaches as far as deep learning is concerned is this idea where you perform your training on an artificial neural net and then you use some optimization process and convert that into a spiking neural net. So in general, I believe the activations are kind of referred to as the rate of the neurons activations, the firing rate, and in some of the nice advantages of this are, well, we're seeing state-of-the-art performance in most of the complex tasks that use spiking neural networks, right? Training very deep networks is made super simple as well, so that's quite nice. Now, Shichi's group, they came out with a paper at ISCAS this year, which basically did this with a 20-layer autoencoder, and they were able to perform segmentation on real-time video filmed from a car. So that's really cool. The paper that I've referred to here is coming out of Bodo's work from back in 2017, the SNN toolbox, which does this whole process in TensorFlow. And what I think is really cool is that it's still quite popularly used today. So I guess 4 human years is something like 400 deep learning years. It's insane how fast ideas come and go, but his tool, Bodo's tool, is still stuck around. So that's got a lot of respect for that. Now, a couple of cons here is that just by nature of converting a neural net, a non-spiking neural network into a spiking neural network, your SNN is an approximation, right? And so it's very, very unlikely that your spiking neural net is going to hit the same accuracy as the original shadow-trained neural network, right? So that's one potential con here. Another one is that, right, a lot of the benchmarks that have taken place on this shadow training approach are not temporal in nature, right? A lot of the benchmarks are still CFAR10 ImageNet, very static images, things that don't quite exploit some of the temporal benefits of spiking neural nets. So that is fairly underexplored. I think there is some work out there, but it doesn't seem to be the dominant majority there. And of course, it's biologically implausible. I mean, I don't think that's a huge issue if you're able to get good benefits on hardware, because at the end of the day, you do have, you're restricting layer-to-layer communication to ones and zeros. So that's really nice. That's something that you can extract a lot of power latency advantages out of. But nonetheless, the fact that you need to take multi-step approach to generating the spiking neural network it could be improved. We could do better, right? So there's several other works that in this field, in this space that I've got to kind of attribute. So Chris Elias Smith and Abronil Sengupta, amongst others, they've done a lot of interesting work in this field. I highly recommend looking up their papers and checking that out. So the alternative approach is sort of, I guess, natively training spiking neural net, which is, of course, what the focus of this talk is going to, of this tutorial is going to be. Now, some of the advantages is that, well, we're no longer bound by the upper limit of artificial neural network performance. And I suppose I've listed this as a pro, not so much because it's a pro, but rather I suppose it, by definition, beats shadow training, right? Now, there's the propensity for biological plausibility of your learning rule. Why is biological plausibility good? Because biology is good, because power consumption is good, because evolution has optimized biology for us in a sense. Now, although backpropagation of the gradient is perceived to be quite implausible, I still want you to keep in mind that backprop is made up of many constituent steps, right? For example, a loss metric can be argued to potentially be plausible in the sense that perhaps predictive coding in the brain, where you take an input, and if your expectation doesn't match your reality, then you update your belief or you update your synapses. Some of the more biologically plausible algorithms such as STDP, spike timing, dependent plasticity, and Hebbian learning, these unsupervised approaches. Now, these are insanely efficient and they're directly inspired by experimental results. They're deeply fascinating, but they really struggle with more complex tasks. I suppose that's because they're more focused on extracting correlations, right? There's no signal to guide them, in a sense. Now, the traversal of an error signal is suboptimal, right? The brain is very unlikely to memorize every single forward pathway. And so transmitting that error is almost definitely not what happens in the brain. But, you know, if we massage it a little bit, perhaps we can find elements that are similar. Now, so yeah, if we have an input, we have an output backpropagating through that network. It's implausible to think that we can find exactly what weights we need to branch out to. So this, what could be more feasible in an order differentiation framework. Now, if you're familiar with order differentiation, you've got reverse mode auto diff, where you calculate the gradient, I suppose, in a backward pass. And alternatively, you've also got forward differentiation. So that's where you calculate your gradient at each subsequent step. Now, most packages, most auto diff frameworks use reverse mode because it's more efficient. But my point here is that it's still plausible to calculate a gradient during that forward pass, right? So how can we transmit an error signal and use that in a forward sense? Well, of course, we've got feedback connections in the brain. So we could potentially use that to update what's going into the spiking neural net. Now, some of the cons here is that hardware as it presently exists is not optimized for spiking neural nets, right? Because SNNs are time varying, and because they're time varying, they're often not as efficient as conventional artificial neural nets, at least during the training process, if you're using something like backprop. And in addition to that, I guess in my experience, they've been very, very sensitive to your hyperparameters. You change one thing, then everything else kind of goes out of whack. So these are problems that we're trying to overcome at the moment. Now, one kind of elegant idea merges all of these, and it came out of Kaushik Roy's group and published to ICLR last year, where what they did was they used the shadow training approach, they converted it into a spiking neural net, and I suppose in a sense they used that as transfer learning. They attempted to, I guess, overcome that upper bound on accuracy or on performance, and then they trained the spiking neural net using, or retrained that spiking neural net natively, right? So I think that was a really elegant approach. And I suppose that their results kind of seem to just match what the conventional spiking, what the pre-trained network gave them. I think the improvements were quite marginal, but still, I think there's definitely some utility there. Now, I guess that where I'm going with this is that gradient backpropagation is honestly, it is a terrific algorithm, and because it effectively works, right? It has its flaws, it scales terribly, but it really does work. And because it works, I guess that led me to sinking in an insane amount of time into what initially was just a COVID lockdown project intended for myself and a few lab mates to have a bit of fun with, to test out a few ideas with. And then I started writing a series of tutorials, and hey, it turned into snnTorch, where finally the graphic design classes I took in high school finally paid off, right? So it's a gradient-based learning framework or Python package using spiking neural nets. You've got the URL below. That's an open source project on GitHub. If you want to avoid spelling my convoluted last name, I'm sure if you simply Google snnTorch, it'll give you the results that you see. We've implemented several quite unique features into it, as well as well-established classical features. So one of the more exciting ones includes real-time online learning, or at least pseudo real-time, insofar as what backprop allows you to do in real time. It's seamlessly integrated with PyTorch, as several other SNN packages are as well. And because it's integrated into PyTorch, of course, it's CUDA accelerated. But we've also come up with a few nice techniques to make it lightweight enough for a CPU, right? So if you're running many, many time steps, then that tends to lead to out-of-memory errors if you're on a limited compute bandwidth. So we've tried to address some of these. So I guess if you want to get started with it, then you can do this in your own time, and I'll give you a link to the tutorials at the end of the presentation. I guess this is a complementary presentation to what I've written up. In Linux, of course, you would go pip install snnTorch in your command line, and you'll be able to install the latest version of snnTorch. In Mac, it's pretty much the same. So with Windows, you've got to be a little bit careful. It's pip install snnTorch with a slightly different system prompt. So small difference. Now, let's move on to Spike encoding. But before we get into how to actually work with this neural net, we need to talk about what we're trying to get the network to do, what we're going to feed as an input, what we're trying to get as an output. And I suppose that historically, there's been this huge war waging on between rate codes and temporal or spike timing codes. It's kind of this sacrilegious situation between those two communities, and kind of like Bayesians and frequentists constantly at each other's throats, right? So what are they? Well, very crudely, a rate code is when you take information and you store it in the spike count or the firing rate. I'll probably use these interchangeably. Just know that there are specific formal definitions that probably mean that these two definitions shouldn't be interchangeably used, but for the sake of simplicity, that's what I'm going to do. And of course, a temporal code takes that information and captures it within the timing of the spike, right? Now, of course, if all these spikes are identical, it's the timing that should matter. So in general, rates are better for error and for noise tolerance because you're distributing or ameliorating your information over time, over multiple spikes. So if one of those spikes fails, then that's okay because you've got many more spikes where that came from. And a second kind of practical thing that I've kind of realized in my own experiments is that it actually enables faster convergence when using backpropagation, because with rates, you're encouraging more firing. And if you have more firing in your network, it turns out that you have a stronger gradient signal. And I guess we'll get to that. We'll get to that in more detail. At the moment, you'll just need to take my word for it. But then a temporal code or spike timing is far, far better for power efficiency and latency, right? I mean, there's different ways you could interpret spike timing. If your spike occurs very early, then you may interpret whichever neuron to have spiked early to be the correct predicted class in a classification or supervised problem. So I don't really want to get into the whole war that's waging on between these two crowds, but I have to say that Bruno Olshausen published a really, really nice paper that still holds up, I think, back in 2004, titled, "What is the other 85% of V1 doing?" Right? Now, in that paper, he conjectures that due to metabolic and power consumption and several other arguments, 85% of the brain necessarily has to be operating on a temporal code, because if every neuron was to be firing at a rate, if information was captured in multiple spikes, then your brain would overheat, burn, and turn into an oven. You don't want that, clearly. So yeah, he makes a really, really compelling case for temporal codes. So I'll leave that with you to mull over, to look deeper into. But having said all of that, we're quite confident that the sensory periphery, at least, captures input information from the external environment in a rate, right? And that rate is transmitted to the brain, and the brain most likely computes that rate or converts it, meshes it, does whatever it does, but it does so in the temporal domain. Okay, right? So yeah, moving on, I want to show you how we can apply that to a neural net. I've kind of black boxed this and simplified this network down to just an input layer and an output layer, knowing that this could generalize to multi-layer networks. Now, say we've got this with inputs coming in from down the bottom and outputs coming from the top. Now, we first acknowledge that spiking neural networks are time varying by nature, right? We'll go into that in more detail, but for now, just accept that they're time varying. And because they're time varying, if we were to pass in some sort of static data, such as a sample from the MNIST data set, we'd effectively have to repeat that sample at every single time point. It's not super exciting, but that's how it would work. Now, the input, if we really want to exploit this, we want our input to be time varying. So let's convert that MNIST sample into something that resembles a rate. Now, of course, I've got a little code snippet of what it would look like to convert a static input image into a spike rate, into a firing rate, with the same dimensions, just projected along a new axis to represent time. Right? And so this value would be projected, this probabilistically firing input sample would be projected into the network with a different spiking pattern at every single time point. Right? And so that's, you're effectively turning strong pixels or pixels with high values into having a high probability of firing, and pixels with very weak values into those with a low probability of firing. So in that sense, it's turned into a probability. And all that takes is importing the SparkGen module from snnTorch, and calling the rate method, passing in your input image with 100 time steps, how many ever time steps you so desire, and away you go. So a similar approach can be taken for temporal coding using the latency function. Now, with temporal coding, more intense inputs, or inputs with a brighter luminance, or whatever your measure of intensity is, are going to simply fire first, right? So this is kind of a blink and you'll miss it situation. So I don't even know if Zoom can keep up with this, but if you see this brief flash of the number 4, then that's what's being projected into the network at a very early time, and kind of the rest of it's just a bit of noise, some of the darker pixels that are firing a bit later, probably meaningless, not going to teach the network too much. So just to capture all of that in one nice big scene, in one nice big illustration, we've got rate code. A dark input corresponds to 0 probability of firing. A bright input corresponds to a very high probability, or 100% chance of firing at every single time step. And this is kind of the in-between 50% case. In the middle column here, we have temporal codes, where a bright intensity means an early spike, and vice versa. A dark means a late spike, or no spike at all if you so desire. I'll add in delta modulation into the mix as well, because this kind of comes into its own class of things, where if you have time varying continuous input data, you basically compare subsequent time steps, and if the change between those two time steps is sufficient enough, then that triggers a spike, right? So I guess here we've got a small increase, and I suppose that's thresholded high enough to trigger a spike. And likewise here. And if you so wish, you could have off spikes, and this just kind of takes inspiration from the way the dynamic vision sensor or the silicon retina camera works, where it's all about generating events from changes in luminance. Okay? So yeah, with all of that being said, that's what I want to say about the input. Let's move to how we might encode data as spikes at the output, or what we want to train our network on, right? Because these are two decoupled things that I think that beginning or novice practitioners in deep learning kind of get these mixed up. So input and output encoding are two very separate tasks that you need to address separately, that need to be addressed differently, right? Now let's say that we've got an output layer. Let's say that this highlighted neuron is our correct neuron, or that neuron represents the number 7, and it's the correct class. That's what we're looking at, right? Now, a rate code is simply going to mean that this neuron fires the most frequently, be it from a count or a rate. The temporal code will suggest that this neuron fires first. The concepts are the same, but we're just applying them in different senses. So in one case at the output, in the other case at the input. Okay, so yes, let's see this in action. We've converted this static MNIST into a spiking MNIST sample. And on a poorly trained network with 2 layers, again, I'm not sure if latency can handle it, so maybe I'll need to skip to the end of this animation and pause it. Not sure if that's updating, but I'll describe it to you. But what ends up happening is that the number 3 ends up firing the most frequently, with number 5 closely behind it. Right? And that number 5 kind of makes sense because this 3 looks like a 5. But what I want to say is that the fact that we're using a rate code here makes it tolerant to the errors that arise, to the fact that the number 5 is spiking quite a lot as well. If we use a temporal code, there's really nothing stopping that number 5 from spiking first, and then 3 overtaking it subsequently, right? So with all of that being said, now that we know what we're trying to get our network to do at a very high level, right, we'll take a bottom-up approach and I guess look at the leaky integrate and fire neuron. So yeah, how does a spiking neuron behave? Well, I guess we'll start with a bit of history, right? So, well, I guess before the history, I forgot I had the slide. We will take a kind of qualitative approach to this neuron. We have several spikes coming in, and if the neuron is sufficiently excited, then it triggers its own spike. Right? So how does it do that? How does it, I guess, integrate these inputs temporally and trigger that spike? So let's take a look at the physiology, or the I guess, material structure of a neuron. We'll fly through this. This is by no means a complete classification of what a neuron is, but yeah, it should be sufficient to understand why it works. So a membrane surrounds the outside of the neuron. The neuron body is, I guess, protected by this lipid bilayer. On the inside of that lipid bilayer, or the membrane, is a saline solution, and on the outside is the extracellular medium, which is also a saline solution. What's nice about saline solutions is that they're full of ions, right? And I guess we can consider ions to be charge carriers. And so in a sense, we could simply model them as a wire. We have 2 wires, one on the inside and one on the outside, and they're separated by this membrane insulator. So if you have 2 wires separated by an insulator, some electrical engineers out there, that's basically a capacitor. Now, concurrently, we've also got ion channels opening up, and we've got pores opening up. And this kind of allows diffusion to take place, where certain ions leak outside, other ions leak inside. So that's modeled with a resistor, right? Because if you have ions moving, you have charge movement, then that's a current, right? So we have a capacitor and we have current flow through a resistor. So what does that look like? Well, something like that. It's an RC circuit, and this current source coming into this leaky integrate and fire neuron model is representing all of the other inputs from higher up neurons in your network. So I guess this reflects those incoming spikes to the animation that we saw before. So let's see what happens exactly. Well, the first time the link between the leaky integrate and fire neuron was made to the RC circuit, it was way back in 1907 by Louis Lepic, right? And he basically stimulated this frog nerve extracellularly, because back in 1907, building current sources was extremely tough. Single neuron readings were also next to impossible. So it was a very crude setup. But he stimulated this frog nerve extracellularly, and he varied the amplitude and the duration of the current pulse. He measured the time it took for the frog's leg to twitch. So that timing, it turned out to be something that resembled an exponential relaxation of an RC circuit, right? And so there's some conjecture that Lepic actually cooked and ate the frog after his experiments. So it's nice to see that recycling was also important back in 1907. So let's see what happens with this RC circuit, or this leaky integrate and fire neuron model, right? We apply a step current pulse, and like I said, this exponential relaxation towards the steady state value is how this membrane voltage responds. Now, I say this with the caveat that the membrane voltage should actually be at a resting potential of -70 millivolts or something around that. And that's typically modeled using a battery, just a DC cell battery in series with this resistor. But I've omitted that simply because it's just easier to follow. So yeah, what if we were to clip this current input, right? Well, what could we expect would happen? Well, I guess life is causal, voltage response is causal, so we expect everything up until that point to stay the same, right? And so indeed, that's what happens. Now let's deliver something that looks like the same amount of charge, so we'll increase the amplitude, but half the time that we apply that current for. We see a faster rise time, but the same decay time, right? Because that decay time follows an RC time constant. We'll do the same thing, again, faster with the same decay. And in the limit, where I guess this is physically an impossible experiment, but if we were to integrate, I guess, the area under this and obtain the charge delivered, then you could get something that actually does make sense. And yeah, we get this non-physical immediate rise time with that decay that follows, right? So what I want to do here is now just apply only that spike train, only those kind of Dirac delta looking functions. So what happens there? Well, our membrane potential is integrated over time and we get the leak. So we see that integration, see that accumulating, and we also see the leak. So we've got two of these covered so far, just got the fire left. Now, in practice, what I want to do is to make this more compatible with a neural network is discretize everything that we see, right? So we've got this in continuous time. Computers are all in discrete steps, neural networks and current neural networks, and everything sequential is in discrete steps. So let's try and do the same thing with membrane. So I've intentionally avoided a lot of the math here. Again, I'll direct you to the tutorials if you want that level of detail. But for now, let's keep it qualitative. Let's keep it interesting. So we've got this discrete representation of the membrane voltage. And apologies if you see this referred to as V or U. I probably use them interchangeably. Now, we can represent the voltage at the subsequent time step as the voltage from the previous time step multiplied by some decay rate beta. Now, beta is a function of R and C, the resistance and the capacitance, and that is also added to the input current. So if we say that the membrane voltage initializes at 0, then the voltage at the next time step is also going to stay at 0 until the current is injected at the input. So that's what we see here. We see this current spike. Let's say it's just a 1. That 1 is going to be added to this next time step of voltage. And if we take that input current back to 0, then you just kind of get this cycle where your voltage is just going to decay, where the ratio between subsequent steps is going to be beta. So if beta is less than 1, then you get a decay, and that ratio there is beta. Okay? Now, let's add in the firing mechanism. Okay? The leaky got the integrate, now let's fire. So this theta is kind of like a thresholding mechanism. So if we apply a similar spike train, then what we see is the membrane potential, the mem, is going to hit the threshold at some point. The moment it hits the threshold, it suddenly triggers that action potential down its axon, and it triggers a spike. So that spike is kind of external to this RC circuit, but it's still there, and we'll see where it goes in a moment. Right? Now, if we kind of encapsulate that into our leaky integrate and fire neuron model, we put that into our little node, then we've effectively captured our, LIF neuron model. So I want to give you a couple of other depictions of what this looks like. Right? So I've gone through this equation here, and this second one here, the spike, the occurrence of a spike, is dependent on whether or not your membrane voltage exceeds your threshold. So this H is the heavy side step. If your membrane exceeds a threshold, then you get a 1. If it does not exceed the threshold, then your spike is a 0. So this is what it what the data flow in a sense looks like. Your current is injected. That current contributes to a membrane potential. It checks, hey, have I exceeded the threshold? If not, I'll just loop back around. The spike is 0. As I loop, then I'm going to decay by a factor of beta. At the same time, I've got my input coming in and it's accumulating. It's being added to that decayed voltage. And then they come together, go back to check if there's a spike. If not, then you just kind of loop again and again. So that's a recurrent representation of a leaky integrate and fire neuron model. And what's nice about that is we know that we have recurrent neural nets. So we can kind of recast this in what looks like a recurrent form, right? Now, another way to visualize this whole process is to unroll the computational graph, where as you move to the right, we're increasing in time. You're increasing your steps in time, okay? And what you've effectively got here is your current going in. If it exceeds your spike, then it goes past here, but in this case, it doesn't. So it just keeps decaying by beta. It keeps decaying by beta. So here we've got a decay of beta cubed. And finally, if your input is sufficient enough, then you get a spike. Here I've shown that to be at t=3, kind of arbitrarily, right? So yes, you've got the recurrent representation and the unrolled computational graph representation. And these two things are equivalent. I find that this representation here is a lot more lenient towards understanding how backpropagation works with spiking neural nets. Okay. Now, of course, we want something to be learning, right? We haven't really gotten to any learnable parameters yet. Of course, beta could be learnable, but I'll leave that out for now. The way we inject that learning, the parameter for learning, is simply acknowledging that this input current can very well be a function of another input x that's weighted by w. W is your parameter, it's your neural network weight. You multiply these together, then that becomes your input current. Now, of course, you could have many, many inputs here that are all summed together, but that's where your learning comes in. And if you're familiar at all with PyTorch, this is simply a fully connected layer that can be represented by nn.linear. You can concatenate that with a leaky integrate and fire neuron, snn.leaky. So we'll get more into that soon. Really quick bit of code here that just shows, all right, let's define a leaky integrate and fire neuron. We'll call that leaky with a decay rate of 0.5. And we set this argument to be true because we want the hidden states of that neuron, the membrane potential, to be initialized. And if you want to construct a neuron model, well, we define a sequential model, first layer being a linear layer with 784 inputs and 10 outputs. And that 10 outputs is fed into this LIF neuron, this leaky integrate and fire neuron. So syntactically, leaky is just treated as an activation unit, and it automatically scales to the number of inputs that are passed to it. So just by definition of having this 10 here, these 10 output neurons, then we've got 10 leaky integrate and fire neurons connected to them. And of course, you can extend this indefinitely. Now, to run that model, you would put it into a for loop because, of course, this is a recurrent network. You want to train it over various steps. So for step in range num steps, so you would iterate over and over until you exhausted all of your steps and you had a long trace of your spikes. Right? So, of course, we have this network. We've captured the neuron, but like I said, we want the output to mean something, be it a rate code, be it a temporal code. We want the correct neuron class at the output to do what we want. And in order to do that, well, of course, we need a loss function. So in conventional artificial neural nets, typically your correct class might be passed through a cross entropy loss, through a softmax, where your correct class is pushed towards 1, as close as possible to 1, and everything else is kind of suppressed. Well, I mean, we take inspiration from that, but there's various ways to implement a loss calculation with spiking neural nets. So let's dig in a little bit deeper. I'll give you a few examples of how this might occur, how we can define various loss functions. All of these have been automated in the module snnTorch, but I'm more concerned with explaining how this works than how to code. So if we consider, I guess, a three-class problem, and we've got three different output neurons. Let's say that this green one, this neuron 0, is our correct class, and 1 and 2 are our incorrect class. So I've integrated a method called cross-entropy rate loss, where all you're doing is counting the spikes at every output, and you pass that count to a cross-entropy loss function. So that's a softmax and then a negative log likelihood. So what you're effectively doing is you're trying to maximize your correct class count. So 5 spikes is trying to be boosted up indefinitely, just as high as it can, while the incorrect classes are trying to be minimized. Okay? So cross-entropy rate loss, and there's several other methods I'll briefly describe. In mean square error count loss, what you instead do is set a target spike count for correct and incorrect classes. And this is the approach that Sumit and Garrick took in their Slayer algorithm that was published in Neurips, and we'll talk more about that soon. 5 spikes, let's say hypothetically we want our correct class to trigger 4 spikes and the incorrect classes to trigger 2 spikes. So neuron 1 is happy. This neuron is not contributing anything to the loss function. It zeroes out effectively. Whereas this class has 3 spikes, and so it's going to try and be suppressed. Why would we do this? Wouldn't it make more sense to use a cross-entropy rate loss and try and boost this as high as possible and suppress these as much as possible? Now, the problem with that is that when you suppress a spiking neuron from firing, the easiest way for your network to achieve that is to simply zero out all of your parameters, or zero out the parameters that are connected to that neuron. Now, if you're zeroing out your parameters, then that could lead to a multitude of problems to do with vanishing gradient or dead neurons. Effectively, zeroing out the activity of a neuron makes it a lot less susceptible to firing, and that can actually be quite problematic. So if I recall correctly, I believe that Slayer achieved state-of-the-art performance on a range of tasks by setting a firing rate that they had a predefined number of steps for each task, and they said, all right, I want my correct class to fire 80% of the time, and my incorrect classes to fire 20% of the time. So that was the ratio they used. I imagine that your network would be quite resilient to the precise ratio that's used there, the precise count, but it's still a parameter that can be played with. Finally, the mean square error membrane loss. So I like to consider this as to be micromanaging the membrane potential at every time step. So rather than applying a loss function to your spikes, we're now kind of cheating. We're looking into the neuron and we're looking at what the membrane potential is at each time step. And effectively, what that means is, let's say we've got 0.9 volts, and let's say our threshold is 1 volt. If we hit 1 volt, then the neuron spikes. Okay? In the MSC membrane loss, we want to encourage this guy to go to 1 volt, and we want to suppress these a little bit. At least neuron 2 needs to be suppressed. I can arbitrarily set my target to be 0.25 to, again, avoid any vanishing gradients or dead neurons, just to have them ready to fire once the correct sample comes in. But we can apply this loss at every single time step. And because we have an indefinite number of time steps, we can actually change these targets at every time step. And what that means is that it doesn't need to be, you don't need to specify 1 volt for every single step, which would encourage your neuron to fire at every single time step, which may lead to a lot more power consumption than you actually need. So this can be really useful for temporal codes, where you set your target to be something higher at the very start of your simulation, and then you suppress it back to 0 or 0.25 as time goes on, right? So I call that micromanaging the membrane, because you're being very particular about the activity. So again, that's very implausible biologically speaking, but that's okay. We're more concerned about functionality at the moment. Another little feature is L1 sparsity regularization, where you have a loss and you add a penalty that comes in the form of accumulating all spikes. And so if you add that term to a loss function, then what you're effectively doing is encouraging your network to spike less. So while still trying to get these values correct, it's also going to be penalized for firing too frequently. Right, so all of those functions and several other losses that are probably a little more boring are are all very, very easy to implement and documented quite thoroughly in online tutorials and in the, I guess, read the docs documentation. So we've got a loss, we've got this recurrent representation of the leaky integrate and fire neuron. Now, I think we're ready to move on to backpropagation and how backprop works on SNNs. Okay, so one of the canonical, so this is not a complete picture of backprop. We're taking a loss function and we're trying to calculate the derivative of that loss function with respect to our weights. Right? A little bit of familiarity with deep learning here will help. But if we can find the minimum of this value, then effectively we can come up with a way to choose our weights W such that this loss term is minimized. Right? And so with recurrent networks, this pathway that you're seeing in blue is just one of many, many pathways. Other pathways could be moving back in time, that's back one step, or you follow the laser pointer back 2 steps or back all the steps. And so there's many, many different ways that we can backpropagate through the pathway. And what you're doing is, after you've come up with all of those backpropagated paths, you sum the gradient at every single one of those paths, and you perform your optimization step using that accumulation of gradients. Now, if that didn't make sense, don't worry about it. I think that what really matters is showing that, well, if I take this first term, DL on DS, so I've said that this is just a function of these terms, because I'm only considering this final pathway for now. We need to also factor in all of these other pathways as well into this function. So this is just one single canonical pathway, okay? Right. So we take the loss, we take the derivative with respect to spikes. And I think that what I relayed in that previous slide about loss functions is that if we change our spikes or if we change our membrane potential, then your loss is probably going to change as well, right? And so there's a direct correspondence between these two. So we can come up with an analytical solution for the loss with respect to the spike. Let's take a look at this third term, dV on di, right? Well, I think it's quite obvious that if I was to increase my current, well, that's just directly being added to my membrane potential. So these two are directly linearly related. And that derivative just evaluates to 1. Very, very simple. Di on dw, I guess we have to go back further than what I've displayed, but that's simply the input x. What I've left out here is this second term. This is the nightmare of a lot of people in this field. But no, many people, much smarter people than myself, have come up with really nice ways to alleviate this. So let's see what the problem is first. If we take a small step or a small change in voltage, if I was to shift that voltage, the membrane voltage, what's going to happen, right? So I said that if the voltage exceeds your threshold, then you emit a spike. If it's below the threshold, then your neuron is quiet. There's no spike. Now, if I take the derivative of S with respect to my membrane potential, well, it's 0 everywhere. There's no change, and then above the threshold, it's 0 everywhere. We just get this Dirac delta at the time of at the threshold. And what that practically means is that, well, for all intents and purposes, the majority of this entire spectrum is 0, right? And so if we backpropagate from S to V, well, this term is most likely going to be zeroed out. And if it's not zeroed, then it goes to infinity or something undefined. And then our gradient kind of breaks down and loses all meaning. And that's very, very undesirable and not very practical at all. So what can we do to get around that, right? Well, there's plenty of solutions that have been proposed. I think you might hear a little bit more about it from Emre at the keynote. Well, a naive implementation of a spiking neuron is, of course, incompatible with the backprop algorithm. So the ways that have been addressed, that have been used to address this, the most popular by far, and what I think is the most practical, the most efficient, the most reliable, simply the use of surrogate gradients. Technically, everything is a surrogate, given that it's non-differentiable, but what the most popular approach here is to simply smooth out this heavy-side step function into something that could be a sigmoid, it could be a fast sigmoid, it could be anything that, I guess, fits the bill, anything continuous, right? And if you do that during your forward pass processing through your spiking neural net, you continue to use the non-differentiable heavy side step because you still want your spikes to be ones and zeros. But during backpropagation, you replace that non-differentiable function. You replace the Dirac delta with a nice smooth version that's defined across effectively all of your voltage, right? So you're only approximating the gradient during the backward pass. And that's a really efficient, that's generally yielded all of the state-of-the-art accuracy and performance of basically everything that I've seen for natively trained spiking neural nets. An alternative approach here is the spike operator. I came up with this myself, and I guess some of the results are good, some of them are negative, but I think it's worth exploring just to show you what's, I guess, worth playing with and what's not. But what the spike operator does is it treats the two regions, the superthreshold and the subthreshold regions, as two separate operators. What do I mean by that, right? So to illustrate, let's consider the max pooling operator, where if we have an input, let's say A, B, C, D, perhaps these are pixel values, and we want to condense our representation of that input, we pass it through a max pooling operator to kind of remove the noise. So we pluck out the largest element of this matrix. Let's say, for argument's sake, that largest element is A. So we pass it through. Effectively, what you're doing, you're multiplying it by an indicator function that's, I guess, 1 for A and 0 for everything else. And it passes A and zeroes out B, C, and D. Now, when we backpropagate through that function, well, of course, the gradient of A is 1 because A times 1 is 1. B, C, and D have all been zeroed out, and so those gradients are 0. Now, one thing that's worth noting is that this indicator function here is actually a function of A, right? So if the maximum value of this matrix were to change, then this A would change as well, right? Then we would have to multiply it by 0, 1, 0, 0. Now, the problem with that is that this operator is now non-differentiable as well. And so in practice, a vanilla PyTorch implementation or TensorFlow implementation of the max pooling operator simply detaches that operator pathway from your gradient calculation. So I guess normally you would see these two pathways meet and they would be summed together and then continue back propagating. But no, that's not what's going on. We're flipping that away, we're snipping it off and killing the operator, making sure it doesn't contribute to the overall gradient, but it still works. The spike operator takes inspiration from this. Well, let's say that we have a spike. Let's say our membrane potential is a 1. Therefore, we expect a spike for a threshold of 1. Now, that 1 is going to be multiplied by a 1 in order to give, I guess, a spike, which is also a 1. Now, if instead our input was sub-threshold, then your output would be a 0. So you're multiplying it by 0. So in the same way, this is sort of like a pseudo derivative where we're removing the gradient from the backward pass. But effectively, my point here is that during this backward pass for a super threshold membrane, your gradient is 1. If it's below the threshold, your gradient is 0. What's the what does that mean? It means that your spike, the existence of a spike here, whether that's 1 or a 0, is actually going to end up being your gradient. So in order to arrive at that result, we're making two operations. So yeah, of course, we're making two approximations. So of course, the operator is treated as independent of the input. That's clearly a lie. That's not the case at all, but it still works. And secondly, the maximum membrane voltage is the threshold. What I mean by that is that, let's say this membrane was to go beyond the threshold, say it was to hit 1.2 volts, right? Well, your output is still 1. So clearly, the operator is not going to be 1 because 1.2 is not going to directly pass and end up as 1. Instead, we make the approximation that your time steps are infinitesimally small, the evolution of your membrane is continuous, and if you're comfortable with that assumption, then your membrane should never exceed the threshold, or at least within the bounds of discretization. So it hits the threshold and then it resets back to 0. So the result here is that the backward pass gradient term is equal to the forward pass spike. If you get a spike on the forward pass, then you get a gradient of 1. If you don't get a spike here, then you have a gradient of 0. That's extremely memory efficient, because you're getting your gradient at the same time as your forward pass. Now, in practice, this actually results in a very odd trade-off that I found between the dead neuron problem and vanishing gradients. So just speaking from a practical perspective and getting rid of the theory, I ran this experiment on something simple, so MNIST. I tested it on the MNIST dataset, and it was able to outperform surrogate gradients or smoothed out gradients, right? And I was kind of confused because, well, if your gradient is 0 whenever your neuron is quiet, then shouldn't that lead to the dead neuron problem? Shouldn't that make training much harder? Well, as it turns out, if you think about it, what you're doing is you're treating your gradient as a heavy, you're effectively saying that my gradient is the same as the spike, and the relationship between your membrane and your spike was that heavy side step. Now, if you think about the rectified linear unit, which is, I guess, 0 if it's negative and a linear function in the positive regime, the gradient of that is also the heavy side step. The reason ReLU works so well is because its derivative doesn't saturate. Now, if you think about the sigmoid function, well, as you go too large or if you go too little, then your gradient starts to converge towards 0. ReLU doesn't do that for positive values. And so ReLU has been used to train super deep neural nets because it effectively helps with vanishing gradient problems. And Timing Her has basically developed a whole initialization scheme for weights based around that concept. So I figured that using this gradient was helping with vanishing gradients. But the moment we went onto more difficult tasks, such as fashion MNIST, which isn't inconceivably more difficult, then surrogate gradients suddenly started to outperform this spike operator as well. So overall, I would recommend using smoothed out surrogate gradient functions, but there are ways to help boost this performance even in the face of the dead neuron problem. And we'll get to that towards the end of this. So one concept that was recently published by Dan Goodman's group, he came out with this concept of sparse spiking gradient descent, which kind of merges, I suppose, the spike operator and the smoothed out approximated fast sigmoid kind of approach, right? It's a hybrid of the two approaches. And what he's done is introduce a new hyperparameter, which clips the gradient to 0 at some arbitrary value, right? So instead of having a surrogate gradient that goes all the way down to, that smoothly goes down to 0, you just clip it. This kind of makes sense because I suppose that here you're getting more accuracy, your gradient is closer to the actual value. I suppose there is a trade-off with some dead neuron issues, but they seem to get some really nice performance as well. Overall, I think a network is probably capable of learning around these little things, around these semantics, but yeah, overall, all of these options are available. If you want to integrate a spike grad gradient, then all it takes is, I guess, defining your spike grad as a surrogate.fast sigmoid. Alternatively, if you want to implement this sparse spiking gradient descent, well, call it a sparse fast sigmoid, and you can parameterize it with B. So that's all I want to say. Talk about, I guess, hacking the gradient. Let's go and backpropagate through time. So previously we only backpropagated through individual steps. Now let's go all the way through time. And this is what that looks like, I suppose. You're taking your loss function and you're taking your error signal, sorry. And as we know, going from S to U, we now have a way to get around that. We know how to overcome that non-differentiability. But let's add some extra details here. So we only looked at one single pathway at a single time step. If we go back in time, right, well, the temporal connections, I guess what would typically be regarded as recurrent connections, is this pass of membrane potential of its decay through beta. If we backpropagate through that connection, the derivative of the membrane at some time step with respect to its previous time step is just beta. The difference between these two is always going to be beta, regardless of what happens. And if we were to jump back further and further in time, I guess you just multiply your betas as many times as you need. And because beta is a value that's less than 1, then your gradient becomes weaker and weaker the further back you move in time, right? So if I was to calculate a gradient that only considered this time step at t equals 3, then yeah, we would expect a fairly large gradient value, just assuming that all conditions held constant throughout the network. A single time step is going to have a fairly large gradient. If we backpropagate through one time step, then it's going to be scaled by a value that's less than 1. If we backpropagate through 2 time steps, beta squared is going to be the decay factor. And if we keep going, then you effectively get this diminishing gradient that demonstrates that an input here is going to have much less effect at to a time point that's projected further into the future, right? So the gradient from I guess the end of your simulation run will become much, much smaller at the start of your simulation run. So if you think about the forward propagation of membrane potential, or if you think about the decay of membrane potential over time, you've just got this exponential relaxation. Now, if I take, well, this should be t plus 1, or sorry, t should be fixed, which let's say t is fixed here, capital T is fixed at t equals 3. And if we move back in time, then the derivative of the membrane with respect to itself at a previous point in time is going to decay exponentially. Now, what I think is incredibly fascinating about this idea is that if you think about local learning rules such as spike timing, dependent plasticity, or Hebbian learning, you've got this concept of neurons that fire together, wire together. So say we had an input spike at t equals 2, then it's going to be significantly more related to the output spike at t equals 3, whereas a spike at t equals 0 is going to be substantially more decoupled from an output spike at t equals 3. So again, this backprop through time, in a way, subsumes what STDP is doing in a very structured mechanism, right? Because the weight update in the end relies on the gradient that you're calculating. And so the modulation of your synapse is going to be very similar to what those exponential curves of STDP look like. I think that's a really fascinating idea. And you might have come across spike response models or filtered or using convolutional kernels, such as, Slayer with Garrick and Sumit's work. In that instance, they use this alpha function kernel, where the convolution, the gradient of the convolution was the correlation. And so in that instance, they're replacing this beta, this regular repeated operation that decays everything in a constant fashion, where as you move back in time, you kind of see that alpha function in reverse, where again, a spike at a very early time is going to have a very small effect on a present time spike. In fact, if you hit the maximum point where, I don't know, perhaps it's t equals 2, perhaps t equals 2 is your max of your alpha function, that's where your gradient is going to really contribute towards your weight update. So that's a simple implementation of backprop through time. PyTorch kind of handles a lot of that. If you want to run backprop through time for many, many time steps on a limited resource, but on a limited compute budget, you run into several problems, right? Because 1,000 time steps for me, for something as simple as MNIST, will often lead to out-of-memory errors on a GPU unless I distribute it, unless I become extremely rich and buy many, many parallel clusters, etc. So one thing that we've implemented into snnTorch to help with lightweight processing is an alternative way to perform backprop through time. You might be familiar with it. It's called truncated backpropagation through time, where you take a subsample of your time steps, you perform backprop through time, and then you process the next subsample. So you're effectively dividing your total number of time steps, and that is extremely helpful for managing memory for long training runs. Now, on one extreme of truncated backprop through time, where if we were to say, instead of subsampling multiple time steps, let's only subsample every single independent time step one at a time. And that kind of looks like this. So we forward pass, and then we backprop simultaneously. Forward pass, backprop. So this approach, it's very, very good for, I guess, managing memory, but you're starting to neglect temporal connections. So I guess that's a drawback of this very naive implementation of real-time recurrent learning. Now, one thing that I should mention here is another interesting point is that because actually last night I was simulating a variation of RTRL, of real-time recurrent learning, and just because I could, I said, hey, let's try and crank out 5,000 time steps. Something ridiculous. I mean, I'm used to running 25 time steps before my computer crashes. So let's try 5,000 time steps. It's no problem because at the end of this backward pass, you get to flush out all of your gradients, you get to flush out everything, most things from memory, and then just rinse and repeat. So I decided to go ahead and for every batch, I would simulate this thing for 5,000 time steps. And using, I guess, the Atom Optimizer, which is quite commonly recommended for recurrent neural nets, what I found was that for 5,000 time steps, you're updating, you're performing backprop 5,000 times. So you're kind of overfitting for an excessively long time range of time steps. You end up overfitting if you go too hard on a single batch of data. So in particular with Atom and I guess stochastic gradient descent with momentum or any method that has some sort of learning rate decay or weight decay, by the time you reach your second batch, you've already done backprop 5,000 times, right? And so there's a need for constraint. There's a need to not go to balance the number of time steps you simulate with, I guess, the optimization method that is used. Now, one final thing that I'm really excited to, I guess, put out there, something that I'm currently working on, is this forward propagation of the gradient idea, which approximates backprop through time, where you take your real-time recurrent gradient and you do that update at every single time step, then you project your gradient through that beta. You scale that gradient through beta and you accumulate it with the next time steps gradient. And if you keep doing that, what you'll notice is, again, you get this approximation of backprop through time that still considers the temporal relations of your data, or of your input spikes to your output spikes, but you're not having to store every single gradient at every single time step. So again, that ends up being really memory efficient and does quite nice things that will far surpass a very naive implementation of real-time or single-step real-time recurrent learning. Right. So I guess that's the pathway of backprop. And if I was to show you some clunky-looking code, we've already seen most of this. Instantiate a neuron, instantiate your model. Again, a fully connected network connected to a leaky integrating fine neuron. Let's define an optimizer, right? We'll call the Atom Optimizer. And our criterion, well, SF is SNN functional, where we use the mean square error count loss that I was previously explaining. Now, you can simply call backprop the real-time recurrent learning method from the backprop module, pass in your network, which is your model, pass in your data loader, number of steps, etc. And it kind of does all the hard work for you. Of course, you've got the flexibility to go in there, do the tweaks that you want. In that case, you would replace the sequential model with class, if that makes any sense to you. But otherwise, if you want a really quick slapstick implementation of a spiking neural net, then snnTorch kind of enables that and takes a lot of the hassle out. So I guess take a look at some neuromorphic benchmarks, because, well, if we're passing in data into our network, I've only referred to MNIST, some really, really simple toy data sets. Some other neuromorphic benchmarks that are available in snnTorch, which are basically adapted from Emre's project, Torch Neuromorphic. They consist of neuromorphic MNIST, where Garrick took a dynamic vision sensor camera and filmed what emulations of saccades of the entire MNIST data set. Got the DVS camera to make sudden erratic pan and tilt motions in order to get that motion of your MNIST data set. That's one example of a very common neuromorphic benchmark that's used. And there's also the DVS gesture data set by the IBM guys published at CVPR several years ago. Yes, what you're seeing here is, I guess it's a right arm moving, I think, anti-clockwise. So these data loaders have been provided in snnTorch, again, thanks to Emre's work that he's done. Also included another really, really cool data set that was presented by Friedman and Zenke's group called the Spiking Heidelberg Digits data set. Now, I think this data set is really, really nice. So what they've done is, in fact, it's like a spoken MNIST data set where they recorded people saying the numbers 1, 2, 3 They passed it through this artificial cochlear model, which consists of 700 neurons. And those 700 neurons would then spike in response to the spoken recordings of these various digits. So I think this is a really, really cool data set that's definitely worth checking out. The process of downloading it and incorporating it into a data loader has been basically the hassle if it's all taken out for you. So I guess that I want to talk about some of the more, I guess, advanced concepts in spiking neural nets that have helped me with boosting performance somewhat. One of them is population coding. So remember when I said that the spike operator really struggles to perform on difficult data, on difficult data sets or excessively deep networks because of the dead neuron problem? Population coding is actually a pretty nice way to kind of circumvent or overcome that, right? Now, population coding is very, very common for local learning, so spike timing, dependent plasticity, etc. But what's a fairly common practice that I've seen is rather than saying, okay, hey, I've got 10 output classes, there are 10 digits, therefore 10 output neurons. Instead, what you might do with population code is allocate, say, 100 or 1,000 neurons, and you would pass your input data through your network, and you would say, all right, cool, let's take a look at all of the neurons that are most excited by a certain class. Now let's allocate that batch of neurons to that class, right? So that's a very common approach to STDP or local-esque unsupervised learning. But what I want to say is that it's also a great fit for deep learning. Now, it's used in practice by some of the Intel and IBM neuromorphic researchers that I'm familiar with, but I haven't seen it formalized in too much detail in a backprop context. So like I said, let's say you have 10 output classes. Perhaps we want to assign 10 neurons to each. So 100 output neurons, and what you'll do with those 100 output neurons is, well, accumulate all spikes. So when you're counting up spikes, take all of the spikes from those 10 output neurons. So what this means is that a distributed representation of outputs or of neurons or of data will effectively exponentiate the number of pathways available for error back propagation. So that's one extra output layer, another one, another one, another one. So we can keep going. Now, what's beautiful about this is that if I take a loss function, that loss is going to back propagate not only all through one neuron here, but it's also going to back propagate through laterally through these other neurons. So you end up with significantly more pathways. Now, what does significantly more pathways means? It means that you're a lot more likely to have some sort of gradient signal available to help with updating your neuron. Now, the fast sigmoid surrogate gradient kind of alleviates this issue as well. It provides a continuous gradient. It avoids, or at least helps avoid dead neuron problems. But the spike operator gradient, that was something that really struggled with deep networks. And in my experiments with population coding, in doing that, in using a distributed representation, you could suddenly see a very low resource gradient calculation method, again, competing on more difficult data sets. And so I guess across 5 simulation runs, I'm going to be very qualitative about this, but across 5 simulation runs, it was very difficult to tell the difference between the fast sigmoid and the spike operator data set. Now, another issue with surrogate gradients in the continuous sense, like I said, is that as your membrane potential goes too high or goes too low, your gradient will also start to vanish because, well, that's why we moved from sigmoids to ReLU functions. Again, population coding could potentially ameliorate that. Sure, some of your neurons may have a vanished gradient, but other neurons may very well still be able to provide a gradient signal that can help learning to take place in your network. Right? So ultimately, population coding can significantly ameliorate the dead neuron problem. It distributes the cost burden of back propagation over space and also in time. Right? Now, I guess close to wrapping up here to leave a bit of time for discussion and also to give everyone a break before what I expect will be a really fascinating talk by Emre at the keynote, is axonal delay. So as far as I'm aware, I believe that, again, Sumit and Garrick, quite partial to their work. Slayer was perhaps the first work that presented an implementation of axonal delay in spiking neural nets. Now, of course, we have temporal connections that can capture some semblance of time dependence in data. But if you think about it, well, we could strengthen that. I mean, conventional neural nets might use gated recurrent units or LSTMs, which can propagate inputs over time until it's ready to either flush them out to the next layer or to just completely forget them because your network has for some reason decided it's no longer useful. Well, I guess that this axonal delay implementation in Slayer is a rather rudimentary but very useful form of that. And I believe that it's a strong reason as to how they managed to achieve such nice metrics on the DVS gesture dataset. So if you think about it, you might have a spike. That spike may not necessarily be flushed directly. I guess we can represent that spike with this blue dot. So rather than passing it directly, the network might learn to add a delay over several time steps. And what you set as that learnable parameter is the number of time steps in which that spike needs to be delayed before propagating to a subsequent layer. So I guess we'll start wrapping up things a little bit early. I suppose I've talked exceedingly fast, but yeah, a few future features that I want to implement into snnTorch include this forward gradient propagation method. All our tests have passed, and I can expect that to be online in 2 weeks, which is, I guess, in a sense, memoryless. And when I say memoryless, I don't mean your GPU isn't using memory, but rather we no longer need memory about historical gradient in order to implement backpropagation. So it was actually super fun to watch my computer be able to churn out 5,000 time steps of simulations without really breaking a sweat. I mean, not super practical, but it was fun to watch. Next, predictive coding, self-supervised learning in a SNN context are also, I think, extremely valuable tools to add. There are a lot of companion tutorials available at the documentation for snnTorch. I guess this is not something that you can click, but again, snnTorch tutorials, that kind of dives into all of the gory mathematical detail with a lot of interactive code snippets that you can play with. And of course, there are several other really cool gradient-based learning SNN projects. I think snnTorch was mainly developed with initially for the intention of just playing with our own research ideas, which then kind of expanded out to saying, hey, well, why don't we have other people play with our ideas? Why not teach them in a somewhat accessible way? So I think snnTorch is great for education, but yeah, there's several other packages and modules that also do really, really nice things. So of course, Slayer, they're working on this kernel filter-based axonal delay spiking neural nets. Very, very easy to work with, very nice and plug and play. SPyTorch by Friedemann. I think that's a very, very incredible body of work and actually forms the basis of several modules in snnTorch. So a lot of credit goes to him on that, even if he doesn't know it. Spiking Jelly, which came out of Peking University, I highly recommend checking that out. It's they're doing things like reinforcement learning, and they've integrated so many impressive features that are just really worth checking out. Rockpool, which implements learnable delays, deep continuous online learning by Emre and Norse. So a lot of cool things going on at the moment. Might be hard to navigate, but hopefully that kind of gives you an idea of what these packages are doing, what their purposes are, how backprop works. To wrap up, I've got several acknowledgements. My supervisor, Professor Liu, contributors, Shinshin and Vinny, and it's Emre, Dusok, Garrick, Sumit, and Friedemann, whether you know it or not. Huge source of inspiration to building snnTorch and teaching me. And so, yeah, with all of that having been said, I'm happy to open the floor to discussion, perhaps give you a small break before Emre's keynote. So yeah, I guess Malika, you can help me stop talking for a little bit.
Thank you so much, Jason. That was really, really nice and really insightful. A lot of things. And I'm sure you need a break right now. I hope you can sleep tonight with so much excitement and adrenaline that goes in you right now.
I feel most sorry. My girlfriend is meant to be asleep, but you know, she told me.
All right, so I think we can, yeah, we can see if anyone has any questions, and please feel free to, I guess, unmute yourself and ask questions. I mean, I can start with, oh, yeah, Katie wrote that you can also write in the chat or raise your hand. But I can start. I have many questions. I guess one really trivial question is first, so as you mentioned, there are many libraries and there are many people, well, there are a few people working on this. So if you, in like a really summarized, in a nutshell, what features do you think snnTorch has that, let's say, no other library brings?
Yeah, so I guess converging backprop towards something that, I mean, isn't necessarily biologically plausible, but at least pushes in that direction, in the sense that you don't need to perform backprop all the way to through your history. Your gradient is literally the spike itself. I mean, it's not like the brain is keeping track of approximate surrogates. It's not to say those are the best approaches, right? I mean, at the end of the day, one of the main goals here is simply just functionality. But if we wanted to do what the brain is doing, I don't know how much backprop we'd be playing with, right? But yeah, trying to at least see if we can, trying to see if we can fit a circle into a square hole. Yeah, so the online learning stuff, forward propagation of gradients, I guess, parameterization of and gradients as well. I think a lot of what's novel about snnTorch are basically those things.
Okay, so actually that was really, really nice. This idea that you have with the, I don't know what you call it, the gradient up, I don't know.
Spike up,
basically,
I don't know either.
Right, spike up, yeah. Spike up, yeah. And I thought that was really, really nice. The other question actually I had was about this population coding, which was, I think it's a really nice idea. It completely makes sense. The only thing I wanted to ask you was, so do you, I guess you introduce some kind of randomness or variability between neurons? Because I guess otherwise they're all doing the same thing.
You're full of great questions, Malika. Yeah, so is what you're getting at, how do you decide what class many output neurons fall into? Is that what you mean?
No. Basically, I'm saying that you're saying that you have a so for each class you now have multiple neurons, right? And then I guess there's some difference between these neurons because you mentioned that, for example, these the gradients can come at different times, or some of them might have the problem of vanishing gradients and some of them don't. And I guess that to me means that they are different.
Yeah, so yeah, I guess the neurons are indeed going to end up being different. They're probably going to behave differently.
No, but are you learning also the parameters of the neurons?
When you say the parameters of the neurons, you mean the weights?
Yeah.
So yeah,
threshold, let's say time constant, threshold, that's what I mean.
So the threshold is fixed at the moment, that's fixed. If there's utility to making it learnable, okay, let's do it. Time constant, that's just a matter of passing in weights that are learned. Instead of setting beta to be a scalar, 0.5, 0.9, whatever the hell you want, you set that to be a learnable parameter. You set that to a learnable tensor. So I haven't tested out learnable neuron parameters directly for population coding, but hey, I guess that'd be a worthwhile research question.
Mm-hmm. Yeah, definitely. And so we have actually one question from the audience. Alexander Johns, I think, is asking, is there a built-in SCDP learning rule that is usable in snnTorch? And great talk, by the way. So.
It's very kind, thanks, Alex. Short answer, no, there is not. I think Brian too handles that. Don't need to reinvent that wheel.
Okay, are there any more questions? I have maybe, oh, we have one. So Shruti is asking, hi Jensen, thank you for the great talk. Can we build SNN of any topology using snnTorch?
Almost any. Look, if you're concerned about residual connections, convolutional connections, basically anything that you can concatenate with an activation in PyTorch, then yeah, you can use it. The beauty of, I guess, the way that these neurons have been, these spiking neurons have been defined, is that when you take an input into that activate, that pseudo activation, it automatically constructs the size of that layer, of the spiking neuron layer, based on the input that's being fed. So if you have additional residual skip connections, or if you have some high dimensional convolutional output, high dimension, I mean 4 dimensions or 3 dimensions, the spiking neuron will automatically adapt to whatever its input is. So I want to say, yes, you can build SNNs for any topology. I'm sure there are some edge cases that I have not thought about though. So yeah, if you find them, let me know.
Yeah, that's really nice to have the community also kind of test out the library and also let you know. Okay, Mariam wants to ask a question, I guess.
Hi, sure.
Hi.
So hi, Jason. Hi, Malika. I enjoyed your talk. Thank you very much. So I have a question regarding the time and latency aspect of snnTorch. So a lot of time when I walk in the domain of conversion-based training algorithms, especially ANN to SNN, especially, for example, the hybrid approach that you also mentioned from Purdue, a lot of time the main issue that I have is that the training time and latency and the number of time steps required to train the network is just huge. So you started with, I don't know, 5 epochs, and it takes you the whole day to just complete that 5 epochs. So can you please comment on the training time you're required to use snnTorch?
Yeah, absolutely. I haven't formally characterized it by any means, but say I can give you ballpark estimates. All right, let's say we take a really simple task. Let's say a 6-layer conv unit. Training it over several hundreds of epochs on a GTX 1080, which isn't great, 8 gigabytes of memory. If I set the number of time steps to be, say, 50, batch size of 128, that might take me, huge variance here, but I want to say between 4 to 8 hours. If I have, that is a huge variance, so sorry about that. If I have a fully connected network, maybe two learnable layers, in that case, yeah, it's super fast. Each epoch, 30 seconds for MNIST. Very, very simple tasks that I'm giving you, but I think that it's totally plausible to run this stuff on a CPU as long as it's not too dense. The moment you take it on a GPU, then it's, yeah, not so unreasonable at all. Yeah.
Thank you very much. So the other question that I have from you is that I think the snnTorch, the testbed is ready. You talked about a lot of different approaches for calculating gradient. So my question from you is that how easily you can switch or incorporate other gradient-based training algorithm inside snnTorch. So for example, compare a slur, hybrid, your approach, because do you see that in future or even current version of snnTorch?
Yeah, I think it's extremely algorithm dependent. So something like Slayer, I can quite confidently say not easy. Because basically what they're doing is a kernel-based approach, which relies on, rather than the previous time steps. So here it's recurrent. I think that's what a lot of the current SNN PyTorch-based packages do. Some sort of time, your current state only depends on your previous state. Slayer kind of scans across all of time with that kernel. It's got to keep track of what point of that alpha function kernel is the gradient for every single time step. So it's quite compute heavy. I mean, obviously the results seem to be quite worth it. So something like Slayer, not easy. Something like, I think, deep continuous online learning that Emre's put out, and if it can be boxed into this recurrent representation of neurons, then I think it should be quite straightforward. In terms of the user, I hope that partially answers your question, but in terms of the user, say you want to switch between RTR, real-time recurrent learning, full backprop through time, truncated backprop through time, that's a matter of changing a word. For you, it's easy. For me, it's a pain.
I can tell. Awesome. Thank you very much. Thank you.
No, all good. No, thanks for your questions.
Okay, we have another question from Chen Li, asking, hi, I would like to ask about whether the conv layer can be efficiently represented and trained by backprop in snnTorch.
Yeah, I think so. I mean, efficiently compared to what? But yeah, I guess accuracy for benchmarks is pretty consistent across what everyone else reports for, I guess, all the toy data sets. And like, I haven't given you accuracies because I think that's besides the point. But yeah, there's no problem if you do a big parameter search. Yeah, convolutions and SNN units are no problem.
Okay, another one, Elkin is asking, have fixed point numbers been tested instead of double point numbers? Does the accuracy decrease?
Yeah, so other people have tested it. I'm lazy, so I haven't. I've got to go keep my girlfriend happy. No. So fixed point numbers, will accuracy decrease? I think that's a huge function of, I mean, okay, this is coming from, I guess, a non-spiking background here, but in general with deep learning, I guess you see fixed point numbers versus high precision values. When does your network suffer big time? Okay, and thank you, Emre. Emre saved my life. Float 1632. Bless you. What I was going to say was that if you have a very big over-parameterized network that is tolerant of errors, yeah, quantize the hell out of it, no problem. I think IBM actually showed binarized performance on DVS gesture of over 90%. So, I mean, that's one extreme. So I think that if you have the patience, then, and if you've got the GPUs to search for that space, then yeah, quantized training is commonplace.
All right, I guess we should maybe let you go sleep. I have another question, but
hit me. We've got, yeah, hit me.
I mean, actually, maybe it's like it's an evil question that has not much to do actually with your tutorial.
All right, I'm going. See you later.
No, it's just that, you know, in the beginning, you were, let's say, you were saying why SNNs are useful and kind of encouraging people to use SNNs because you know, so you can represent numbers as binary, and then basically your multiplication becomes a memory read, right? But then my question for you, I mean, I don't know the answer to this question, and I'm also in the same boat as you are, and I think that maybe this is the right place to talk about it, although it's very late where you are. But if the multiplication is really for free, computation generally is free, right? I mean, what the problem is really memory access and bringing data to where you want to do the computation, but the rest is really, so if then, you know, based on what you said, rate coding actually gives you more accuracy, converges faster, and at the end, if we are to use rate coding, would there really be an advantage in terms of energy efficiency or power efficiency using SNNs?
Yeah, that's good question. I think I have an answer for it. So if you think about it, right, memory accesses suck regardless. Non-spiking, spiking, you're going to suffer from that one way or another, whether you like it or not.
But if you want to represent a number with if it's just a number, you read the memory once, right? But if you want to represent that number with a rate, then you have to access the memory multiple times.
Yeah, so I think that kind of goes back to the question of what are SNNs good for, right? I mean, if you're trying to represent static values, then which you only access your memory once, go deep learning. Don't use SNNs for ImageNet. What's the point? If it's for, I guess, sparse spiking data, that's a good fit. Perhaps even multimodal. I think that there's some really cool work out of ETH on multimodal hand gesture classification coupled to EMG signal recordings, those, like the accuracy of that multimodal setup outperforms the equivalent deep learning of high precision values. So my point is that it's still equal. if you allocate it to the right task, if you stick to purely temporal tasks, you're still suffering from the same number of memory readouts. Maybe I'm wrong, but that's how I see it. Rate coding.
I just wanted to ask you because, I mean, this is generally a question, and since you brought it up, and you know, you had a really insightful talk, so I'm sure you talked about this before. So yes, I thought to ask you what you thought about it.
Yeah, well, that's what I think. Another factor that you have to consider, I suppose, is that all right, the readout is one thing, but communication is extremely expensive, right? I think that you end up, well, with deep learning chips, the biggest cost of it is, all right, when you have an architecture that's too large to handle on, I guess, one single core, and you need some multi-core unit or multi-chip unit, you need some die-to-die interfacing, the latency to go from A to B is where you start to suffer from an architectural perspective. In that instance, sending high precision values from A to B, spiking neural nets, sending ones and zeros from A to B. That communication saving, rate coding, temporal coding, doesn't matter, just the fact that that's ones and zeros, I think that could be a huge, huge benefit no matter what, right?
Yes, I agree, 100%. Thanks a lot, Jason.